All right, good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Thank you. Great, so last time we spent the whole class showing that you could define an isomorphism between the integers and the fundamental group of the circle by sending each integer to omega n, which is just the path that goes around the circle n times, either counterclockwise if n is positive or clockwise if n is negative. Right? And we showed this was an isomorphism, and this came down to studying the covering space given by the real line over the circle. Okay. So what we showed was that given any path in the circle, you could lift it to a path in the real line, and it was unique as soon as you picked where you were going to lift the base point. And the same was true for homotopies. Okay, that's what we did last time. Any questions on last time? Okay, great. So now that we have a non-trivial fundamental group, we will start by seeing some consequences of that. Right? So the first one, as we anticipated last time, is the fundamental theorem of algebra, which says that if P is any any polynomial in the complex numbers, then either P is a constant or it has a root in the complex plane. Okay. Wonderful. So as you know, this theorem took a long time to prove. It was, I think, D'Alembert in like the 1730s who first tried to prove it. And then Gauss famously in his PhD thesis starts by saying, it's a very important theorem. Nobody's given a proof. Here are 4 different proofs. Right? And they're not quite right, but they're close. OK. Here's a very different proof from what Gauss did. So assume that P, given up in this way, does not have any roots. Right? So what we want to show is that P must be a constant. Right? So degree 0 polynomial. Well, so if it doesn't have any roots, then let G of S be the map where you take P and we want to go around, OK, let's put an R, and let's go around the circle to pi is of radius R. But let's fix things so that you start at 1. So you start on the at 1 on the real line, and then let's fix things so that you stay on the unit circle. Right. So the thing we're dividing by is by hypothesis never equal to 0. So it's OK to do that. And of course, the modulus of this is always 1. So for each r, this defines a loop in the circle considered as part of the complex plane based at 1, at the complex number 1. Right? Okay, they are clearly all homotopic because this is a continuous family in R. And so they are all homotopic. And G sub 0 is the constant loop. Right? So the class of GR in the fundamental group is the same as the class of 0. Right? Okay, on the other hand, if you have a polynomial like this, then a key fact is that if you're far enough from the origin, then the first term dominates. Right? So let's take advantage of that to find a simpler polynomial, a simpler loop, still in the same homotopic class. So let R be larger than both 1 and what you get by summing all of the coefficients. Right. So if we look at the complex numbers at radius r, then the size of the leading term, right, r to the n, which we could write as r times r to the n minus 1, is greater than, well, this number times r to the n minus 1. And that is greater than or equal to a1 z to the n minus 1 plus so on to an. Right, where of course there we're using the triangle inequality, and we're using that r is greater than 1 to say that, oh, well, this one is bigger than r raised to the n minus 2 or r raised to any power less than n minus 1. Okay, so that tells us that if you were to modify these polynomials by putting a t in front of all of the lower order terms, then this does not have roots with mod c equal to capital R. Right? Okay, for any t, for any t in 0, 1. So now take this description of G, fix little r equal to capital R, but change the polynomial by putting in t. Right? So consider call it G sub r of t and s, which is the same thing as before, but now we have p sub t. S p sub t of r divided by the modulus. OK, this is a homotopy. Between G sub r and say G sub r of 0. All right, so what happens when t is equal to 0? When t is equal to 0, the polynomial is just c to the n, right? And if you're just doing c to the n, then this gives you e to the 2 pi I n s, right? And if you write that out, that's exactly the class of omega n. Right? That's just the formula we had for omega n written in complex coordinates. Hence, the class of omega 0 is equal to the class of omega n. But we showed last time that phi is injective. So that's equivalent to saying that n is equal to 0. And that's what we wanted. OK, so if you like, in spirit, it's not all that different from D'Alembert's original attempt of a proof, which actually you can fix to make a real proof. Because D'Alembert also said, well, for large modulus, we only care about the leading term. And then what he said was, look at the absolute value, the modulus of the polynomial, and assume that its minimum is achieved at the origin and is not equal to 0. Then you look at the next term, the first non-constant term. And he said that for small modulus, that's the only one you need to care about. So by comparing the first non-zero term for small modulus with the leading term for large modulus, he was able to show that there had to be a root by the intermediate value theorem. So if you like, it's not that far from the original proof, but it's very slick because we just used the fundamental group of the circle. OK, here is another application, the Borsuk. No, I think we do Brouwer fixed point first. So. Great. So the next thing is a theorem, a very important theorem by Brouwer. Brouwer, you've probably heard of. Well, in Dutch, Brouwer as a word just means a person who brews beer. So you may have heard that. But this refers to L.E.J. Brouwer, who was a mathematician, very famous for the intuitionistic approach to the foundations of math. So this is an approach that claims that you're not allowed to use the law of excluded middle, at least when you're talking about something infinite, right? So to prove that something is true, it is not enough to prove that negating it is false, right? So a similar sort of thing is that if you want to construct a set, for Brouwer, it's not enough for you to just tell me, OK, I'm going to take a subset of this bigger set by this rule. For Brouwer, you have to also show that there is an algorithm that, in a finite number of steps, determines whether or not a given element is in that set. Otherwise, your definition doesn't count. Right? So at the time, it was not very popular. But with the rise of computer science, then well, if you want a computer to define a set, then you really do need to have a finite algorithm that determines whether or not an element is in a set. So now with computer science, intuitionistic foundations make a lot more sense or a lot more relevant. But what's great about Brouwer is that when he was getting his PhD, so 1908 or something, he was already thinking about this, and he couldn't convince his advisor that this was a good idea. So the advisor told him, OK, if that's what you want to do, first you have to make your reputation so people will take you seriously, and then you can do this. So amazingly, in 4 years, he proved an amazing amount of theorems in topology, very important, including the one we're about to see. And as soon as he got tenure, he stopped working in topology. He sort of renounced his theorems because, as we're about to see, the proof is the opposite of intuitionistic. It's reductio ad absurdum, right? So it's going to use the excluded middle to prove the theorem. But yeah, as soon as he got tenure, he renounced these proofs and only talked about intuitionistic mathematics from then on. OK, but here's what his theorem says. If you have any continuous map from the two-dimensional disk to dimensional disk, then you have to have a fixed point. Right? So there is some point that f of x leaves where it was. OK. So this is true in higher dimensions as well. And we will prove it in arbitrary dimensions later. But at the moment, our tool just gives us the one for the disk, the two-dimensional disk. OK, so proof. So as anticipated, we're just going to assume the opposite and see that that's false, and then spite Brouwer by claiming that hence this is true. Right.
So is this his proof?
Almost. Yeah, so it's the same argument, except that he doesn't use the fundamental group of the circle. He uses the notion of degree, which is another one of the things he came up with in those 4 years. But yeah, other than that, it's essentially the same argument. So assume that this doesn't happen. Assume f of x is different from x for all x and d2. OK, so we're going to construct a map, define R from the disk S1. So here's the picture. You have a point x. You hit it with f, and you land somewhere different necessarily, right? So you're going to look at the ray that begins at f of x, goes through x, and then hits the circle, and call that point R of x. Right? So define R of x as the intersection with the boundary circle of the ray from f of x through x. OK? So it's easy to see that R of x is continuous. Because if you were to move x a little bit, then by continuity of f, that's just going to move f a little bit. And then the ray is only going to move a little bit. So I'll let you write down details if you feel so inclined. But here's an important property of the way we defined it, is that R fixes all points on the boundary circle. Right? So in terms that we talked about before, R is actually a retraction. OK? So that's a problem. That's a problem because given any loop, H, into the circle viewed as a subset of the disk, it is null homotopic in D2, right? Because D2 is a convex subset of Rn. So you can always just take the constant loop with the same base point and then take the convex combination and move this loop to that one.
Can you just repeat why any loop like that is null?
Certainly, yeah. So what you can do is take h sub t to be 1 minus t times h plus t times the constant loop at the base point, right? And because D2 is convex, this stays inside D2, right? Okay, but then R composed with h sub t is a null homotopy in the circle starting at R composed with h naught, which is R composed with h, which is just h, because h takes values in the circle, and R is the identity on the circle. Right? So what we've done is we've taken an arbitrary loop on the circle, and we've shown that it's null homotopic. Right? But that's not true, because the fundamental group is not trivial. Right? So this contradicts right? So we've reached a contradiction, and that finishes the proof. Our initial assumption must have been wrong, because we do allow the law of excluded middle. Okay, so fixed point theorems are wonderful because they give you existence, right? It's really hard to prove existence. That's, if you like, why the proof that the fundamental group of the circle is not trivial was difficult, because we had to prove that something existed, and we had to do it by constructing it little by little, right? So when you have a fixed point theorem, then that's a really strong tool you can use to prove that things exist. So, if, for example, solutions to equations exist. Okay. So the next application is Bork-Ulam, and it's set. Bork-Ulam. So these are Polish mathematicians. So Brouwer proved his theorem in 1910 or so. These are Polish mathematicians who proved this in this next theorem in like 1933 or something, so shortly before World War II. So if you think back, this is a wonderful time for mathematics in Poland. This is when Banach was there, and they had the whole Scottish cafe thing going on. Unfortunately, things did not go well for Poland in World War II. And so Borsuk stayed there and tried to keep the University of Warsaw going like completely underground. They would just meet in coffee shops and stuff and have classes there for the students who were still around. Ulam went to the United States, and he was very influential in creating the hydrogen bomb. But before that, when they were in Poland and life was good, they showed that if you have any map from, I guess I went S2 to R2. Must have antipodal points where it takes the same value. Right, so that is, there exists some point in S2 such that f of x is the same as f of minus x, we're putting S2 inside R3 so that we can use vectors to reflect. Okay, so to see why this is surprising, if it's not immediately surprising, so think of S2 as being the Earth, and take any two measurements that you can assume are continuous, like wind speed and temperature. And this says that at any moment, there are opposite points on the Earth where those two measurements are exactly the same. Okay, so and again, this is true in higher dimensions as well, but we'll get there eventually. So the proof is similar in that assume that it's not true. And so let G of S be, so take F of, well, let's say G of X, F of X minus F of minus X, and then divide by the difference. So G takes points on S2, and then this is a vector in R2, but I divide by its length, so I end up with something on the circle. Okay, so great. So again, we want to get a contradiction by looking at classes in the circle. Right? Of course, this is mapping from S2, so it's not giving us something in the fundamental group. But we can just pick the equator, for example, to get a map from S1 to S1 that then we can study in the fundamental group. So let eta be just a parametrization of the equator. So just take S to cosine 2 pi s sine 2 pi s 0, where we view this as sitting inside R3. And take H to be G composed with eta. So now this is a path, 0, 1 to S1. Right. Okay. So on the one hand, H is clearly null homotopic. Right. So it's homotopic to a constant map. Right, and why? Because the equator inside S2 is null homotopic. Right, you can just take the equator and lift it up until you get to the North Pole, and now you just have a point. Right, so so if you give me a homotopy that starts at eta and ends up at a constant map, I can just compose that homotopy with G, and that'll give me a homotopy from H to a constant map. Right? So since with eta t a null homotopy of eta, H sub t equal to G composed with eta t is a null homotopy. Of H. Okay, on the other hand, okay, so if we stare at G, G has the property that if you look at minus x, you get minus what you got at x. Right? Of course, you should think of things as living in S2 or S1. So this says that G takes antipodal points to antipodal points. Right? In fact, maybe, let's say, anti of G of x, well, it's G of the antipodal point of x is equal to the antipodal point of G of x. Right, so what this means for H is that H of s plus 1/2 is equal to the antipodal point of H of s. This is for all. S in 0, 1/2. Okay? So if you just look halfway around, then you're just taking the antipodal point. Right? So what we want to do with this is we want to show that H is not null homotopic. Right? So we're going to think about what this means if you were to take this loop H and lift it to a path on the real line. Okay? So if H tilde is a lift of H to a path in R, okay, we can use the fact that, okay, so let's remember we have the real line winding around, sitting above the circle, we have P. So if you have a point here, and so it lifts to there and there, and there, then if you look at the antipodal point, then it would lift to here and here and here. And it's always, right, to go from an x to an x, you would go a full integer, right? So to go to the antipodal point, that's exactly halfway there, right? So you would go up by half an integer, right? So the fact is that if you look at the P inverse of the antipodal point of something, you get P inverse of x plus 1/2, right? So as sets, this, for example, if this were 0, then these would be the integers, and these would be the half integers. So what that tells us about H is that when you lift, H tilde of s plus 1/2 is equal to H tilde of s plus q over 2, where q is an odd integer. Right? Just because this guy is in this set and this guy is in this set. Right? Notice that this q, we justify its existence at every s, and in principle that means that it could be a different q for different s. But of course, this is continuous and this is continuous. So this q, if it were a function of s, would be a continuous function of s, valued in the integers. And the only continuous functions into the integers are constant. Right? So this q is a constant. It's the same one for all s. OK. Great. So we have that equation. Let's plug in a couple interesting values of s. So if s is 0, then we see that this is true. And if s is 1/2, then we see that this is true. And if you plug this one into this one, you get h tilde of 0 plus q. Right? Now remember that our isomorphism was just pick the lift that starts at 0. Right? So if h tilde of 0 is 0, then h tilde of 1 is equal to q. And since we know that q is odd, it is not 0. Right? So this tells us that the class of h is the same as the class of omega q in pi 1 of S1. And q odd implies that this class is not the class of omega 0. That's a contradiction.
Have you seen the book by someone on the Bork-Ulam Theorem?
I have not.
Borsuk means either beaver or badger, I don't remember,
Uh-huh.
in Slavic languages. And so in that book, instead of the QED symbol, they draw a little badger.
Excellent. Excellent. There is a lovely analytic proof of Bork-Ulam due to Milnor. I've put a link to it on the course website. Okay, here's an easy consequence of Bork-Ulam. So let's say that you take A1, A2, A3 inside the sphere, and these are closed subsets such that the sphere is equal to A1 union A2 union A3. Then at least one of these sets contains an antipodal pair. Okay, so this is also true in all dimensions. So for example, for the circle, this says that if you write the circle as a union of two closed subsets, at least one of them has to contain antipodal points. Right? So you can think that if you were just doing a very simple division into two connected intervals, then, well, since they're closed and they cover everything, then the endpoints are going to be antipodal. And you can see that you need closed, because if you were to allow half closed, then you could just have one of the points be on one interval, and the other point, the antipodal point, being the other one. So we do need closed. Okay, so the proof, well, I want to use Bork-Ulam, so I just need to cook up a useful map from S2 to R2, right? So for each AI, let di from S2 to R be the distance to AI, right? So di of point x is the infimum, or the minimum, among all of the y's in AI of the distance between x and y, where we're using the Euclidean distance by putting S2 into R3. Okay, and then let f of x be d1 comma d2. Okay, so Bork-Ulam theorem, right, before I erase it, implies that there is some point for which f takes the same value on that point and the antipodal point. this is great. So there's a point so that the distance to A1 of that point and the antipodal point are the same, and the distance to A2 is also the same, right? So if either one of these is 0, we win. If they're both non-zero, then both x and minus x have to be in A3, because they're not in A1 or A2. So we also win. Right? So if either of these x and minus x are corresponding AI, otherwise x and minus x are not in A1 union U2, hence must be in A3. Yes?
So can we use this to prove that you can't have a convex polyhedron with only 3 faces?
Convex polyhedron with only 3 faces.
My thought being that you can essentially inflate it to a sphere, and then if one of the sets has an antipodal pair, then you would have a line going straight through the origin, which, if you start by assuming that the origin is in the interior of the polyhedron, that gives you a contradiction.
That might work. No.
So this ends up having potential implications for, like just geometry.
Right. It's certainly, you can do something the opposite of that to see that 4 sets are enough, because you can just put a polyhedron with 4 sides inside, and then it just project out to a sphere, and there are your 4 sets without antipodal points that do cover the sphere.
Tetrahedron, poke a hole in it, get an air pump.
There you go. Exactly. Yeah. Okay. Okay, any questions on these applications? Okay. Right, so as I mentioned, they're true in higher dimensions, and once we have homology theory worked out, then we'll be able to prove them. Actually, I think there's one more thing I wanted to say. Maybe later. Okay. So back to the theory. Great, so here is a simple fact. If x and y are path connected, then the fundamental group of x times y, say with base point x naught, y naught, is the product of the groups. Okay, so this is nice and easy because a map into x times y is continuous if and only if the induced maps into x and into y are continuous. So, of course, by induced maps, what I mean is that you could project onto the left factor, or you could project onto the right factor, and the composition of these maps is what needs to be continuous, right? And this determines the topology, the product topology on x times y. So these are precisely the continuous maps into x times y. right? Well, okay, great. So that means that a loop in x times y is just the product of a loop in x and a loop in y. Right? And a homotopy in x times y is just a product of a homotopy in x and a homotopy in y. Right? So good night. So you could just say, so let's give this a name, pi x composed with f, and this pi y composed with f. So the map pi 1 of x times y, base point x naught y naught, to pi 1 of x naught times pi 1 of y naught, given by sending the class of a loop to the class of the loop in x and the loop in y. Well, first of all, it's well defined, right? Because homotopies correspond to homotopies. And it's bijective, because every map like this comes from a map like this. So this is a bijection. And it is a homomorphism because concatenation here just means concatenate in each coordinate here. Right? And so this is a group homomorphism. And since it's a bijective group homomorphism, it is a isomorphism. Okay, so this is pretty direct. So that gives us a few more examples. That means that the fundamental group of the n-dimensional torus, so here this refers to S1 cross itself n times, right? We use T instead of S because S to the n means the n-dimensional sphere, right? And so to avoid confusion, we use this. Well, so this is then equal to C to the n. Right? So for example, for the two-dimensional torus, well, you have one loop that goes around here and one loop that goes around there. And these are generators of C2, right? And by this proposition, it's just C times itself. So it's a commutative group. Yeah. Once you fix the points.
Right, so like pi 1 x.
That's right. So you're right. I could have just left out the base points. Yeah, I don't think I use path connectedness at all. Okay. So the thing that made, one more thing before we get there. Yeah, okay. OK, here's another part of the theory. So induced homomorphisms. OK, so first, notation. If we say that a map goes from xx naught to y naught, this means that you have a map from x to y, and it happens to send x naught to y naught. Right? So it's faster to just include that in the notation for phi. Right? More generally, so also, if you have a subset of x and a subset of y, then phi mapping the pair xa to yb means that you have a map from x to y, and phi of A lands inside B. Right, so it's just convenient to include that in the notation when you're writing phi. OK, so the point, of course, is that given a map of pairs or of based sets, we get a map from the fundamental groups at these points by taking the class of a loop and sending it to the composition. Of course, you have to make sure that this is well defined, because this is really a homotopy class of paths. But if f sub t is a homotopy between f0 and f1, then phi composed with f sub t is a homotopy between the corresponding images. So this is well defined. Right. Moreover, it's a group homomorphism. Right. So if f and g are both elements here, then phi composed with the concatenation is equal to the concatenation of the compositions, since both are given by the map that sends S to phi of f of 2s if S is in 0, 1/2, and phi of g of 2s minus 1 if S is in 1/2, 1. Right? As you can easily see in either case. Right? So we have this equality at the level of paths. So it certainly survives to homotopy classes. Right? So that's great. Every time you have a continuous map between spaces, you get a map between homotopy groups. Right? The loops you start with are based at some point, and the loops you end with are just based at the image of that point. Okay, some easy properties that are worth pointing out. So let's say that you have x naught maps to y naught, and then another map that sends you to z naught. Right, then since composition phi of f, since composition is associative, we have phi composed with the induced map of the composition is equal to the composition of the induced maps as maps from pi 1 of x naught to pi 1 of z naught. And an even easier fact is that if you look at the identity map of a topological space, then the induced map the identity on the fundamental group, right? Because you do nothing. Yes?
So what this is giving us essentially is some sort of connection, I'm not sure exactly how to formalize it, between some version of the category of topological spaces and the category of groups.
That's where I was going. Yes. Exactly. So these facts are exactly what you need these facts say that the fundamental group is a functor from the category of based topological spaces. Right? So objects consist of a topological space together with a point on that topological space. So you fix a point with continuous maps. Let's say based continuous maps. So our two objects are topological spaces with choices of points, and we're only interested in those maps that send the point in x to the point in y. And the category of groups with group homomorphisms. Yeah. So indeed, all of the things we're going to see both this semester and next semester, so all of the homotopy groups and all of the homology and cohomology groups are all functors from topological spaces to some algebraic category. So it's in a sense, it's even better. So something we definitely will not cover, but later this semester, we're going to introduce the homology groups. So there's a homology functor. And the stuff that Randy McCarthy works on is about like constructing Taylor expansions for arbitrary functors. And so you could ask, well, what's the derivative of a functor? So it's like a linear approximation. And what's a linear functor? A homology theory. So for people who do category theory, homology theories, which is what we're going to study later on in the semester, are the simplest functors, the ones that you approximate everything else by. So yeah, not only is everything a functor, but they're the important ones somehow. Turns out. Okay, great. So next example is the sphere. So pi1 of Sn is trivial if n is greater than or equal to 2. Well, example / theorem. Okay, so this is intuitively obvious, right? Because you give me a loop, I just contract it to a point, and we're done, right? But whereas on Rn, the intuition is easy to carry out, because if you have a convex subset of Rn, you can just contract the whole convex set to Rn. So it doesn't matter where the loop ended up, you just contract the whole thing. Sn is itself not contractible. Turns out there is an n-dimensional hole there that you can't just collapse away, well, without changing something. It's a little harder to carry out to intuition. If things were smooth, that would not be a problem. We would just do the same thing, just follow your nose. But we have to do things for continuous maps. And continuous maps include space-filling curves, right? So you can take a map from Rn to Rm with n strictly smaller than m, and you can cook up a continuous surjective function, right? So that's messed up. And so you have to worry about that here, right? So let's worry about that. Okay, so let f be a path into Sn. So if there's a point x in Sn. So of course I want this to be a based loop. Right, so there's some point x0 in Sn, and both endpoints go to that point. So if there's some point in Sn that is not in the image of f, then it's easy, right? Then since Sn minus that point is contractible, we can compose f with a null homotopy that f is trivial in the fundamental group. Right? So the problem is, okay, what if you don't have a point that it misses, or you don't know that you have a point that f misses? So in general, we'll show that we can homotope f relative to endpoints. So there's a path homotopy to a map that is not surjective. Okay. Okay, so f is based at x0. Pick a ball, say centered at at a point x1, whose closure does not contain x naught. Okay, so let's just stay away from x naught because we don't want to change the base point. We wanted our loops to stay based. But we're going to have this ball, and there's a point at its center x1, and then the path f, maybe entering this ball many times and doing all sorts of silly things. Who knows, right? So what we want to do is modify only the parts of f that go into this ball, and we're just not very ambitious. We just want it to miss the center, right? Just stay away from the center, and then we win, right? Then we just contract the whole sphere. Okay. So if we look at f inverse of b, then because f is continuous, this is an open subset of the interval, and hence this is a union of intervals, is a union of intervals. Could be infinitely many. Okay, but if we look at, so let A1, B1 be the intervals, in here containing point that f sends to x1, then these are finitely many. By a compactness argument. Okay. So on each, if you look at the closed interval, then the f must send the endpoints to the boundary of the ball, right? Because that's how these intervals were constructed. They're the connected components of the inverse image of B. Okay, and now since n is at least 2, if you take the ball and remove a point, then this is path connected. So there is some path that starts here and ends there and doesn't go through the center, right? Of course, this is easy. I mean, you could just stay on the boundary of the ball and go from there to there, because that's connected. But in any case, here's where we're using that the dimensional restriction. And B is convex. So let GI be a path, be such a path. Well, I haven't said one. Be a path in here from f of AI to f of BI. And by convexity of B, these are homotopic. Right, whereby these I mean f restricted to this interval and gi. Okay, so make these finitely many modifications. Replace each f restricted to one of these intervals with a gi, and this changes f within its homotopy class, within its based homotopy class, because this ball does not include x naught, and ends up with a path that misses the center of the ball. Right? So changing f in these intervals produces, say, f prime in the same path homotopy class but with x1 in Sn minus the image of f prime. Hence, null homotopic. Okay. Okay. So here's a corollary. What I started to say a moment ago, what really made Brouwer famous is that he was the first person to show that dimension is a topological invariant, right? So it was surprisingly hard, it turned out, to show that Rn and Rm are not homeomorphic if n is different from m, right? So Brouwer was the one who was able to do that. So at the moment, again, our tools are just getting started, so we can do R2. So R2 is not homeomorphic to Rm for m different from 2. Right? And again, what makes this difficult is that there are space-filling curves. So you have obvious injective maps from Rn to Rm if n is less than m. And you have non-obvious but continuous surjective maps from Rn to Rm. And so you can use that to put together a bijection, but it won't be continuous, right? So, so that's why it was hard to show that, that just in general, there's no homeomorphism between them, right? So proof. So we'll just look what happens if you remove a point. So removing a point disconnects R. And not Rn for n greater than 1. So those are not homeomorphic. OK, so R is not homeomorphic to anything larger, in particular not R2. On the other hand, for R2, well, let's say in general, Rn minus a point, minus, say, the origin, is homeomorphic to Sn minus 1 cross R, or R plus if you like. This is just polar coordinates. Well, of course, something I'm using is that if they're homeomorphic, then you can remove a point from each one, and those spaces will be homeomorphic, right? So let's see what happens if you remove a point. So pi 1 of Rn minus 0 is trivial for n greater than 2 and non-trivial for n equal to 2. Right? And of course, if you have a homeomorphism, then the composition with the inverse would be the identity map, either on R2 or on Rm, depending on which order you do the composition. But if it's the identity map, then the induced map is the identity. And the induced map of composition is the composition of the induced maps. So you would have group isomorphisms between the fundamental groups. Right? So the fact that the fundamental groups are different is enough to see that they're not homeomorphic. Yes?
So presumably if we replace the subscript 1 with the pi with a higher number, we could extend this to showing that higher dimensional real spaces aren't homeomorphic to one another?
That's right. That's right. So next semester, we'll do higher homotopy groups, and that'll work. But later this semester, we'll do homology, and that'll be strong enough to run this argument.
Okay.
Yeah. So let me just point out the thing I mentioned there at the end. Note that if phi is a homeomorphism, then the induced map is an isomorphism. Since if y to x psi is the inverse of phi, then psi star is the inverse of phi star.